everyone. Today we have Maxime speaking on topological Hochschild homology and MacLane homology, a modern comparison.
Right. So thank you, Sarah, and thank you for organizing the seminar, of course. So I'll be reporting on some joint work with GROOT, who's my master's advisor. So yeah. So the topic is topological Hochschild homology and MacLane homology. Let me start with some sort of a warning. I'll be using infinity categories, and well, I think most of what I do can be transformed through models, but for concreteness, I'll be using quasi categories, so the model will fly on Nuri. I'll also be using model categories because part of the results I'll be mentioning are some sort of a bridge between concrete results in the classical world, say, and new results in the infinity world. So I'll be using those. Then some conventions. Oh, right. No, sorry. Spectra first. Yeah, I'll be using a lot of spectra, and you don't need to know a lot about them. You just need to think about them like as some sort of chain complexes over the sphere spectrum. There's a good theorem to justify this analogy, but you don't need to know much more than that. And yeah, so now the conventions. So I'll be using tensor products and limits and co-limits, and those will all be derived by default. So I'll be using like homology limits and co-limits in the infinity world. And similarly, match product of spectra, which is also derived by default, will be denoted by this tensor product of the sphere. And finally, I'll be using abelian groups and chain complexes, and I'll view them as spectra, as Ellenberg-MacLane spectra, and I won't make any notational distinction from the two. Right. Now that's out of the way. Let me state the goal. So the goal of the results I'm going to talk about is to compare topological partial homology and MacLane homology. So there was a theorem by Tirashvili and Balthausen in '92 that already compared the two on the level of homotopy groups. So it states that for any ring R, so here a ring is a usual ring, discrete ring, there's natural isomorphism for RR bimodules M between topological partial homology of R with coefficient M and MacLane homology of R with coefficient M. So of course, don't worry, I'll be explaining what those terms mean. So the goal is to restate and prove this theorem in modern terms. So the way it was proved in '92 used, well, an old definition of spectra. Yeah, and it only compared the homotopy groups and not the actual underlying spectra of the things we're comparing here. And secondly, I'll try to improve it by comparing multiplicative structure on both sides when M equals R and when R is commutative. Right. So now I can start and state sort of summary of the talk. So first of all, I'll be giving a brief introduction to partial homology. So this will include topological partial homology, but also it will be necessary to talk about MacLane homology. Then I'll be talking specifically about MacLane's Q construction, which is necessary to define MacLane homology. And of course, I'll define MacLane homology at that point. Then at the end of this section, I will just state the goal more clearly and precisely. Then I'll outline a strategy of proof for the results I'm presenting. And then I'll state, and well, proof is a big word, but I'll state the comparison theorem and explain how the strategy works, and then I'll conclude. Right. So first of all, partial homology. So what I'm going to present is somehow a generalized version of, well, what we usually call partial homology for, say, flat rings in the usual case, in the classical case. So here, the general setup is we have a symmetric monodal infinity category. For everything to be nice, I'm going to assume all along that C is presentable because all of the categories we're interested in are presentable. And we have an algebra object in it, and M an AA bimodule, which means an A tensor A op module in C. And so now we want to define partial homology in this context. So first of all, we define a simplicial partial object, which is, well, the usual partial object when you specialize to like the usual categories, and when you take A, for instance, to be a usual flat ring and M a usual A bimodule, each has to be flat probably as well, flat over Z. Then you have these space maps, which are the usual ones. So you have this thing where it's kind of cyclic, and you multiply the M here with the first A1, In the middle, you multiply just the consecutive terms, and in this one, you multiply the last two. And you have usual degeneracies as well, which amount to inserting one in the correct spot. So of course, this definition is very like hand wavy in a way, because, well, you can define things that way in the one categorical context, and it's a bit easier, harder to define this infinity categorically, because you can't really define things like on the set level this way, because, well, first of all, tensors aren't well defined; they're only defined up to homotopy. But yeah, but you can actually define this thing infinity categorically, and it amounts to the correct one in the usual cases. And once you have this Hochschild simplicial object, you want to define the Hochschild complex, just like you do in the usual case. How do you generalize this? Well, in the usual case, say you have just A, your usual discrete flat ring, and M, a usual A tensor A up module. And then you have this Hochschild simplicial object, and you take the associated chain complex via, say, Dolphin correspondence. And, well, in DZ, so what I'm denoting DZ here is the infinity derived category of chain complexes. Well, homotopy colimit along delta up, so the simplex category, amounts to taking the total complex. So when you're taking, like, in the usual case, when you're just doing the Dolphin correspondence, this is just what this does. So it's just taking the homotopy colimit. So what this motivates is the following definition of the Hochschild complex somehow in our general setup, is we just take the colimit along delta up of the Hochschild simplicial object. Now, of course, this colimit is derived as usual. So in the usual cases, it gives back what we want. Right, so that's what I said. When A is usual flat ring and M the usual bimodule, then this is the usual Hochschild complex. When A is unflat, this corresponds to what's often called Shukla homology, where you have to derive everything in sight, which some people tend to call partial homology as well. But it's not very interesting for our purposes. Right. And, well, there's a small lemma that I won't prove, but it's another expression for, sorry, wait, there's an arch that should be an A here. Another expression for a partial homology, which is that partial homology of A with coefficients in M is the same as the relative tensor product over A tensor A up of A in M. And here, this tensor below in A tensor A up should be derived as well. That's why there's a difference between flat rings and not flat rings. And the second point of view can also be interesting, especially in case we're looking at the multiplicative structure, because, well, in the first case, the multiplicative structure is not so obvious. But in the second one, when A is commutative, then the multiplicative structure is quite obvious. Right. And so topological Hochschild homology is the case when C, our symmetric monopresentable category, is just the infinity category of spectra. So in this case, we denote it by THH over R and M. So R here is an arbitrary, say, E1 ring spectrum, and M an R tensor R up module. Right. And so this is just a spectral version of Hochschild homology, and somehow it behaves better than usual Hochschild homology in good cases. In bad cases. Say, for instance, over FP, you lose some nilpotence phenomena and stuff like this. Yeah. And it's interesting in part because it relates to algebraic K theory of a ring R. There's a Dennis trace map from KR to THH of R, which can be used in trace methods to compute KR. And here, of course, I said THH of R when I meant THH of R with coefficient in R. Right. So that's a very brief introduction to topological Hochschild homology. There's a lot more to be said, of course, but I think Liam said a few things in his talk, and I think we heard about topological Hochschild homology a couple of times already. But yeah, so I won't go into too much detail into much anyway. So now I can talk about the Q construction, which is the part of the second layer in my talk. So Q is a functor from abelian groups of chain complexes. So it's a functor that was introduced by MacLane in the 1950s. I don't have a precise date because, well, depending on where you look at, well, different dates, but okay, it's not very important. And the definition of this functor is somewhat technical, so I won't mention it here. I won't define it precisely. What's important to know is that it's like a very, very explicit chain complex. Like the definition of the differentials is explicit. The differential, various degree-wise terms are very concrete as well. And there's a universal property to this functor. There's an infinity categorical universal property that I will explain later. And it's part of our work was actually proving this universal property. So this universal property can be taken as a definition, which I will explain later. Right. And so one reason this Q construction is important is that if you let KAN denote the nth element within space for A in a Billion group, then you have a natural isomorphism for a billion groups of between H star of this Q construction of A and the co-limit of these H the homology of KA K. So this here K is moving, so you have the stable homology of the Ellenberg within spaces somehow. And if you so this is a proposition that was proved by MacLane, and the proof was actually later simplified by Topological as well. And if you want to restate this this co-limit here, so if you want to really see the point that it's stable homology of the Ellenberg within spaces, you can just denote it that way. So it's phi star of C tensor over SA, so the stable homology of A. And so this is very interesting because you have this very concrete chain complex, and its homology groups are the homotopy the stable homology groups of the Ellenberg within spectrum A.
Is there any?
Yeah, go ahead.
Is there a relation between the Q construction and for K theory of an exact category, or is it completely different?
Well, I don't see one. I don't really.
No.
I can't tell you that there isn't, but I don't see one.
Just hoping that maybe the MacLane homology is created so that there's an easy map from K theory gets created using the Q construction or something. But yeah, I don't know. Like, yeah. No.
Sorry, I can't answer this.
Right.
Right. So if you see Q of A itself as a spectrum, so as an Ellenberg spectrum, then its homotopy groups as a spectrum are the same as its homology groups as a chain complex. So this second version can be reformulated as follows. So pi star of Q of A is pi star of Z tensor A. And so a reasonable question that you can ask is, does this isomorphism between homotopy groups come from a natural equivalence of spectrum? Yeah, of course, here, this isomorphism of homotopy groups is natural in A. Now, if you know that both are Ellenberg within spectra, then this is even more reasonable because Ellenberg within spectra, just as chain complexes, are entirely determined of natural equivalence by their homotopy groups. So the reasonable question, if you remove the word natural, it becomes the answer is obviously yes, but so adding the word natural is not trivial at that point. Right? Yeah, that's right. So Ellenberg within spectra are determined non-naturally by their homotopy groups. Right. So now I want to define MacLane homology starting from the Q construction. So to do this, we have to have additional structure on Q. So first of all, there's a monoidal structure, which is called the Dixon of products. This monoidal structure, again, since I didn't define the Q construction precisely, well, it might not be obvious why there's such a monoidal structure, but once you see the definition, it's pretty clear where it comes from. Similarly, there's a monoidal augmentation from Q to the identity. So here I'm denoting the identity abusively when I really mean the inclusion from the Billion groups of chain complexes. I hope this abuse of notation is not too problematic. But so there's this natural transformation, which is monoidal. And well, in fact, Richter proved in a paper in 2000 that there was actually an infinity monoidal structure on Q extending the monoidal structure and the augmentation. So it's not a symmetric monoidal structure, but it's infinity nonetheless. Right. And once we have this additional structure, we can define MacLane homology since for any RR bimodule M, since we have this augmentation cube R to R, we can view M as a QR bimodule simply because we have this map here. And so we can define a MacLane homology of R with coefficients in M as the Hochschild homology of Q of R with coefficients in M. So this Hochschild homology here in EZ, of course, because Q of R is not a discrete ring, so you have to do some chain complex thing. Right, and well, so this is all over Z, so in DZ, so in this derived category of the Billion groups, this infinitely derived category of Billion groups. And Q of R is actually always flat as a Z module. So again, I didn't show you the definition of Q of R, but it's clear from the definition that it's always flat. So this just amounts to the usual partial complex if you want a complete model of this fluid. Right. And so yeah, now let me make the point about the commutative case. So if we're going back to the general context, so still in the partial homology, we have this symmetric monoidal presentable infinity category C and this algebra object A. And if we assume further that A is E infinity, so it's a commutative algebra in C, then we can see that the partial homology of A, which we can define as the partial homology of A with A, is this relative tensor product here. But tensor products in E infinity algebras are just pushouts of E infinity algebras. So this tensor product here can be seen as a pushout in E infinity algebras. So it requires a natural E infinity structure as well. And it's actually the same thing if we let M be an E infinity A algebra. We have, sorry, this shouldn't be A, this should be A tensor A up, right? So if we have that M is an E infinity A tensor A up algebra, then we can also put an infinity model structure, sorry, an infinity structure on this partial homology of A with coefficient M. So I'm doing this right because then you'll see that in the cases of interest, so THH and HML, we can have commutative algebra structures on our homologies, and we won't compare these. Right. So now that I've explained, introduced the main players of my talk, I can state the goal more clearly. So recall that Hochschild and Bellhausen provided a natural isomorphism between THH star of R with M. So this star here means symmetry groups, and HML of R with M. And so the first goal would be to prove that there's actually a natural equivalence of spectra between THH of R with M and HML of R with M. And the second goal would be to prove that if we let R be commutative and take M equals R, then both HML of R and THH of R acquire a multiplicative structure. So the second goal is to prove that actually this equivalence here can be lifted to an infinite equivalence. Right. And well, this makes sense only when R is a discrete ring and M a usual RR bimodule, because, well, the Q construction is defined on abelian groups and not on chain complexes. And, well, the natural way, like if you want to extend Q to actually all chain complexes in the infinity sense, then to define Q in a sensible manner, you'd have to do all the work we did, and then wouldn't really make sense because you just sort of assume the result you're starting from. Right. So this is really for R discrete ring, even though THH is defined for more general rings. Right. I think it's a good time to stop and ask for questions. So the tradition is to have cats, but I don't have my own cat, so I use the sheep from Paris 13 University. Are there any questions so far?
So sorry to jump the gun, but are you gonna compare THH and MacLane homology by producing a map from S1 to HC or something?
No, not as far as I can tell. The comparison actually comes from this universal property of Q that I mentioned. So I'll explain this. But, yeah.
I was thinking just because THH is
yeah, it's S1 tensor A. Yeah, but this description only works for infinity ring spectra actually, and the comparison of THH and HML actually works for arbitrary rings. So rings that can only be associated with one. So if you use this description as factorization homology, you wouldn't have.
Yeah, you don't get to. There's no difference between the A and the AOP and S1 tensor definition. Okay.
Yeah.
Right. Cool.
Right. So no other questions? Cool. Okay. So now I can describe the strategy of proof of these results. So the first step is to actually give an interpretation of the Q construction that allows us to state a universal property not only for Q itself, but for its uniform model structure. Because so far, so the description of Q is very concrete, very like explicit, but this is problematic because then we don't have like a conceptual understanding of it. And similarly for its uniform model structure, when Richter defined it, I couldn't tell from her paper whether there was like some hidden universal property. And so we have to somehow understand it more clearly. And so this first step will do that. Then once you have this, you use this universal property in this interpretation to actually prove a conjecture that was made by a bunch of authors. So that's Fyodorovich, Kurashvili, Schwenzel, and Bauthausen in 95. So they conjectured something a bit less general than I wrote here. They conjectured that Q of R, so for a ring R, was equivalent as A infinity ring spectra to Z tensor R. So this follows actually from this more general statement that I put here, that Q as a symmetric monogonal functor is just Z tensor blank. So we'll prove this, which recovers formally the conjecture in this FPSDW paper in 95. And then once you have this equivalence of spectra, this natural equivalence of like symmetrical level functors, the conclusion from there to actually goals is essentially formal. And actually the first part, so the part where you just compare the spectra with no additional structure, was already done in this paper by FPSDW. And yeah, it's essentially formal. Right. So let me just explain. So this formal conclusion. Once you assume the conjecture. So if you assume that we know that Q is equivalent to Z tensor blank as symmetrical level functors from Dillon groups to chain complexes, and if we take R a ring and M an R pi module, then we have that this Q of R tensor n times tensor M, all of this over Z. We can rewrite it this way. And then, well, we have that the Z's here, you can probably see my mouse. So the Z's here cancel with the Z's here. And the first one cancels with this one. So you actually get that this Q of R tensor n times tensor M over Z is just R tensor n times over the sphere, tensor over the sphere with M. And so if you just take the co-limit on both sides, since these equivalences just respect the simplicial structure, you get that HML of R with coefficient M is just HH of R with coefficient M. So that's just essentially formal. It's just somehow base change for Hochschild homology more generally. Right. And so we really see here that the main point really is the conjecture that Q is equivalent to Z tensor blank. And yeah, the proof for multiple degree structure I won't describe, but it's just as easy, it's just as formal. You actually analyze both sides, so HML of R and THH of R as pushouts, and you analyze the maps appearing in those pushouts, and you just prove that they're the same. And it relies on the same thing where the first of Z's cancel out. Yeah, not too hard. Right. Now that I explained how to conclude once you have the conjecture, let me explain how to prove the conjecture. So first we have to, that's the first step, we have to interpret Q. So there's a paper by Johnson and McCarthy from '98. So it was written before we had the whole apparatus of the categories and all the nice results just were there. So it's written in more concrete terms and perhaps less abstract, but this result is already in that paper essentially. So if we have if we let FZ denote the category of finitely generated 3Z modules, so Zn and stuff, and we look at the left adjoint to the inclusion of additive functors, fun plus means from Fz to Dz. So this inclusion preserves limits, and so it has a left adjoint essentially. And yeah, so if we look at this left adjoint, then we can determine Q to actually be the image in this fun plus thing of this Z functor. So what does the Z functor do? It takes a finally generated 3Z module. It forgets that it's a Z module, just remember that it's a set, and then it takes the 3Z module of that set. So this is a functor from Fz to Dz. And if you additivize it in a way, so take the left adjoint to the inclusion, then you get Q. Again, this can be surprising if I didn't tell you what Q was, but if you know the definition of Q, like the explicit model for Q, then you can clearly see that it's defined like the differentials are there somehow to correct the lack of additivity of this functor here, C blank, which is clearly not additive, right? And so this property actually gives Q a universal property. And so it will allow us to actually relate it to spectra via some sort of Morita theory, because this second category here, additive functors from Fz to Dz, can be analyzed quite easily through Morita theory. So the reason why this is the case is that if we look at this functor, so from modules over Z tensor Z, so here, yeah, this is the real difference between sphere spectrum and Z, that's Z tensor over Z spectrum with itself is not just Z, it's a new ring, a new infinity ring spectrum, which is completely different and very interesting in its own regard. And so if you look at, so if you take a module M over this new ring and you tensor it on the right with any Euclidean group or C module more generally, and look at the left Z module structure on M. So you have these two Z module structures on M, and you have one on the right and one on the left. So you tensor the right one and then consider the left one. Then this gives you a new chain complex. And so you have this functor that to M associates this functor M tensor over Z blank, and this functor is an equivalence. So this is essentially just Morita theory. Yeah, and some analysis of yeah, what DZ with the universal property of DZ with respect to FZ in a way. Okay, and so now if we look at both sides of this equivalence, so we have modules over Z tensor Z and additive functors from FZ to DZ. Well, modules over Z tensor Z have a monodal structure, symmetric monodal structure, which is given by tensor over this ring because it's a commutative ring, so its modules have this symmetric monodal structure. And on the other side, you have functors from Fz to Dz, which have a symmetric monodal structure as well, which is given by Day convolution. So it's a pretty standard in one categorical situations. And in the infinity categorical context, it was defined first by Glassman in 2016, and then it was expanded by more books. And this Day convolution is compatible somehow with this left adjoint that I described earlier. So this left adjoint is a reflexive localization, almost by definition, and it's compatible with the Day symmetric monodal structure. So yeah, I could get into details about this. Essentially, this means that if you have something that becomes an equivalence, then you can tensor it with anyone, and it's still an equivalence. It still becomes an equivalence, and this allows you to prove formally that there's an essentially unique symmetric monodal structure on the right, so on additive functors, such that this localization functor, so this left adjoint, is still so the localization is symmetric monodal, and it follows that the inclusion is also less symmetric monodal, not stronger for the inclusion. But so this is very interesting. So because it provides additive functors with actually a symmetric monodal structure, and we know that this additive functor category is equivalent to these modules of Z tensor Z. So we have two equivalent categories with each a symmetric monodal structure. And so then the natural question is, are they the same? And it turns out that we can also prove that this equivalence can be made into an equivalence of symmetric monodal infinity categories. So it can be lifted to a symmetric monodal equivalence. So yeah, this tensor product over Z tensor Z coincides with this thing that's deduced from the Day convolution. It's not exactly the convolution because you have to localize it, but it's, yeah.
Sorry, is there a particular reason why you're throwing an FZ in that left argument instead of a DZ?
Right, so one of the reasons is that right. So if I put DZ here, I would have to put co-limit preserving instead of additive. And so one of the reasons I used FZ was to have a smallness condition, which is necessary for some of the arguments. But actually, the theorem before this one, so by Johnson and McCarthy, is actually true for more general categories than FZ. But yeah, it was useful to have FZ. But you're right. I could simply put co-limit preserving functors from DZ himself. But for instance, to define deconvolution on functors from DZ to DZ, it's not as easy because DZ is large. And so deconvolution relies on some sort of co-limits that are indexed by domain. So you need some sort of smallness condition. But you're correct. Actually, this will come in handy.
Maybe I'm just ignorant of getting around certain smallness problems because I never think about set theory. But is there a harm in, like, we can talk about this later maybe, but I think I'm confused about the smallness being an issue. But we can chat about it later.
Yeah.
in the chat. Thanks.
Sorry. So additive functors from FZ to DZ are equivalent with this sort of deconvolutional symmetric model structure to Z tensor Z modules. And so now the point is that Z blank, so this functor that I mentioned before, is actually the monoidal unit in functors. So not additive functors, but in functors from FZ to DZ. And again, this is true replacing FZ with a lot of things. And it's actually useful to know that. But since localization, so from functors to additive functors, is symmetric monoidal by definition, it follows that Q, so this Q construction is actually the unit in additive functors. And since the unit in Z tensor Z mod is just Z tensor Z, then it's sent to Q as well. And so in particular, we get that as symmetric monoidal functors on FZ, we have this equivalence between Q and Z tensor blank. The reason for that is that, I should have mentioned this, that if you look at deconvolution, if you look at the algebras in deconvolution, then you get lax symmetric monoidal functors from FZ to DZ. So this just follows from the fact that the unit is sent to the unit in as algebras by a symmetrical functor. Right, and so, well, this is not quite exactly what we wanted because this is an equivalence of symmetric model functors in FZ, and we still need to get to abelian groups. But this is not so hard, actually. So to extend it from FZ to abelian groups, we use Ken extensions. And so it's actually pretty easy to see that Q is the Ken extension of its restriction to FZ. For Z tensor blank, it's a bit more subtle. Actually, I thought it was easy as well, but it's a bit more subtle. And it was pointed out to me by someone that you need to work like a tad more than just what seems obvious, but isn't. But anyway, they're both the Ken extensions of their restrictions to FZ. And so Ken extensions can be made symmetric monoidal in a sense. And so you also get this result on abelian groups. So you get that you have this equivalence of symmetric monoidal functors from abelian groups to chain equivalences between Q and Z tensor blank, which is the goal, which is the conjecture that we want to do. In particular, it answers the reasonable question we asked earlier, which was, so we have this equivalence between Q of A and Z tensor A. If this equivalence natural in A, the answer is that yes, it is, and it's even symmetric monoidal. And so also from this corollary follows the conjecture that was made in FPSVW that Q of R is equivalent to Z tensor R as A infinity rings or E1 rings, but they stated it for A infinity same as E1. It's just respect their writing. And if R is commutative, then this equivalence can be made into an equivalence of E infinity rings. And a point that I should mention is that since the algebra structure on both Q of R and Z tensor R actually comes from there being symmetric one-level functors and R being a ring in abelian groups, then this equivalence is an equivalence as Z algebras, not just any ring spectra. And actually about the Z algebra thing, I need to give a quick warning about it, which is that I claim that Q of R is equivalent to Z tensor R as Z algebras, but the right-hand side has two natural Z algebra structures that are not in general equivalent. It's important to know which Z algebra structure we're mentioning, because there's one that comes from this Z factor here. So you just include Z on the left, and you have one that's coming from the Z algebra structure on R, which is just like so Z to R and then the inclusion of R, this tensor product. And in general, they're not equivalent. And the thing is that on QR, there's only one reasonable Z algebra structure. If you don't know this equivalence, there's only one natural Z algebra structure. And so the previous statement is that it coincides with the one that's coming from the Z. So the one coming from the left on this tensor product. One example where they don't coincide is with R equals F2. So on Z tensor F2, there are two natural Z algebra structures, and they're not equivalent in general. Pirashvili actually seems to believe that there should be some rings of algebraic integers, for which this is also the case. So he didn't phrase it by saying Z tensor R. He phrased it with a splitting conjecture for like a splitting formula for Q of R for certain R's, which he believes to be false for some rings of algebraic integers, and this splitting formula would actually follow from the two structures being equivalent, but it's not always true. And I also think it's the case for FP, for rod P. I don't have a proof yet. I've been told it could follow from like studying power operations. I actually asked the question on math over flow, and if you have any thoughts on that, I'd be glad to hear them. But yeah, in general, they're not equivalent. Right. And a second warning, so it's a small reality check that I need to make. We defined an infinimonomal structure on Q, which is, well, it's the unit and additive functor, so it has an infinimonomal structure. And we proved our result with this one. But in 2000, Richter defined another infinimonomal structure on Q, and it may a priori be different from ours. There's no reason to expect a priori. Maybe if you have a functor, you have two natural infinimonomal structures on it. There's no reason to expect that they're the same. But it turns out that the techniques we use to prove the various statements that I included here also prove that the two structures agree. And the lemma, the cute little lemma that this relies on, is actually that you have a symmetric one-level infinite category, and if you have an algebra structure on the unit 1, so let's call this algebra structure A, then you have in particular a unit map, A' from 1 to A. This is a map of algebras as well, of course, as usual, and this is an equivalence. So the statement is that, yeah, so there's up to equivalence, there's only one algebra structure on the unit of the symmetric infinite category. And in fact, yeah, so that's what I said. This lemma was helpful more than once in our work. Let me sketch just the proof of the lemma, which is pretty fun, I think. So first, by passing to the homology category of C, we reduce to the one categorical case. The reason is that the localization functor from C to its homology category just preserves and reflects equivalences, and it reflects, it preserves algebra objects. So if we can prove the statement there, since eta being an isomorphism in this not curly C, then it would be an equivalence in this curly C. And there, we know that the endomorphism monoid of 1 is commutative. So that's just an application of Ekman-Hilton, the usual argument. So if we want to prove that eta is an endomorphism in this category, we only need to prove that it has a retraction, because then there's a commute, and we're done. And in this case, we see that the algebras of algebras just imply that the multiplication map, which is from A tensor A, but also from A, because A has the unit as an underlying object, is such a retraction. So then it's pretty easy to conclude from there. Right. And let me now conclude. I think I'm a bit early. I hope that's okay. So the Q construction that I didn't define precisely, but it's an explicit chain complex model for Z tensor blank. So this Z tensor blank is actually known. It's known to be an Eilenberg-MacLane spectrum, like so it's equivalent to some chain complexes for some other reasons, like the fact that DZ is a second C modules. But it's not known that it has, well, now it is, but perhaps some people knew it, but it's not obvious that it has an explicit chain complex model. And the Q construction is such an explicit chain complex model. And so it's actually a symmetric monoidal model, and it's actually a natural model. So it's not just point-wise model. And this allows this Q construction and the fact that it's equivalent and naturally equivalent and symmetrically equivalent to Z tensor blank allows us to compare HML and THH naturally, and not only at the level of homogeneity groups, which the Kuresh-Vili-Waldhausen paper allowed us to do. And then let me just state one quick reason why this comparison can be useful. So why are we interested in HML and THH? So I explained a bit why we're interested in THH, but why are we interested in HML? Because it seems like a curious construction, and the Q construction is a bit technical. So why is it interesting? Well, the reason is because HML has some various interpretations, for instance, as functor homology. And so there have been some algebraic techniques that have been developed to actually compute HML. For instance, there's a paper by Hochschild and Schwartz, which computes HML of FP. So from this functor homology point of view. And THH of FP is a classical calculation that was originally done by Hochschild in the first paper where he defined THH, but it's not an easy calculation. It's fun to know that there's a second point of view, which is this functor homology point of view. Right, thank you for your attention. And if you, of course, if you have any questions, don't hesitate to ask them.
Yeah, on behalf of everyone, yeah, I'd like to thank Maxime. And then questions.
Do you think so? This Q functor is an explicit chain complex model for Z tensor over S.
Yeah.
Could you get? Do you think you can modify it for like maybe like other abelian groups? So instead of Z, maybe like Z mod 2 or Z mod P.
Right. Well, I guess it's pretty easy because tensor products are associative. So you just need to tensor Q over this abelian group. And maybe, well, if the abelian group in question is flat, then it's just tensoring in the usual way. And if the abelian group in question is not flat, then you just take a flat resolution and tensor it with Q. So I guess, well, yeah, maybe if the abelian group is not flat, this is not very satisfying. But at least for flat abelian groups, it's pretty straightforward from there, I think.
And could you relate these to some variant of THH or?
Oh, that is a good question. Well, right. So if you look back at the proof, which was very early on, of the comparison, not so early, it's there, yes. So if you, for instance, if you tensor, say over a flat ring for simplicity, so let's call it A, then you'd have an A here, right? And so you could put an A here and tensor over A here instead. And you get topological or Hochschild homology as well. So if you take this variant of Q over a flat ring A, and then you take the corresponding modification of this MacLane homology, then you'd still get just THH. So, but
that's very weird.
yeah, but if you still tensor over Z, then I'm not sure what you get. That's a good question.
Are there any other questions for Maxime?
Can you say something more about potential computations that you can do with this stuff? Or like, I don't really know much about this MacLane homology stuff, so maybe why, or like, what's a good reason why it's like sort of maybe more computationally tractable than THH? Or like, are there sort of things that you would like to try, like certain computations you might try to recover with MacLane homology that you know, might try, or like you might conceivably try to implement?
Right, that's a great question. Thank you. So the reason why MacLane homology can be computationally tractable is that it has an interpretation that I didn't actually mention in this talk, but I did sort of work on it in my master's thesis, which is that HML has an interpretation as some sort of functor homology. So it's homology of, say, it's sort of a torque derived tensor product over FR, so the same category of finally generated free module for R. And so you can, I think it's easier in this case to have, like, to find explicit computational projective or injective, in the case of homology, resolutions of your functors that you're interested in. For instance, so this functional Sparks paper actually, like, it works by finding explicit injective resolutions of a certain functor and then working via like some shifting things and for instance, it uses the Frobenius and stuff on some categories. I mean, not on some categories, but on some interesting functors. And so, yeah, it seems that many techniques have been developed in functor homology, over the years. And for instance, I think Pirashvili calculated topological partial homology of Z mod n using this technique, using HML, and then this functor homology. I don't have like a conceptual reason why it's easier to do these algebraic computations than topological ones that are related to THH. But in practice, it seems like it's pretty, like, there has been a lot of work on this. And I saw this comment on Math Overflow from someone saying that they'd be interested in knowing that they can compute HML because it's easier for them. So I could ask this person and actually have a better reply. And perhaps one thing I'd like to say, more on the conceptual side about this thing. So if you're interested in, say, topological partial cohomology, so the dual version where instead of taking the relative tensor product over R tensor R up, take the mapping spectrum over R tensor R up, then you have so you have this THH and THC somehow, and you also have an analog for HML and CML, so MacLane cohomology. And then what's interesting is that HML and CML are easily seen to be dual to one another when R is commutative, but it's not the case for THH and THC. Like, they're dual because of this result, but it's not as easy to see. And yeah, so that might be one reason we're interested in seeing that.
Great, thank you.
Any other questions for this recorded portion? Okay. Well, if not, I'd like to thank Maxime again, and I'll go ahead and stop the recording.